Okay, hello, welcome to another one of my video log recording sessions where I talk about genetic algorithms and stuff like that, and how to make better evolution algorithms, or come up with better ways of evolving entities, solutions. That's what other people would call them, but I call them entities. So, what is the date? The date is right now 2025 March 27th, and the time is 1:50 a.m. and today I will be covering this notebook, General Genetic Algorithm 0, percentage 0.5. I'll get to what this means later, so, I'll explain as I go along, starting now. And the purpose of this notebook is to assess genetic algorithms and evolution, as I'm just reading from here, where the items or genes and their corresponding utility values and constraint values are all generated from a given distribution or two. So for example, if I say 20 items, it'll just give me from item 1 to item 20, and I can somewhat randomly from a given distribution generate the utility values for these items and the constraint values for these items. So the utility values could also be from the same distribution as the constraint values, or they could be different, or it might not matter. That's what I'm trying to find out. So for instance, in this case, in this notebook, the utility values are going to be from normal distribution, and the constraint values are also going to be picked from a normal distribution. And what you see here, max constraint perc, as in percentage, is 0.5. As you see here, 0.5 or 0-5. What this means is that when setting the max constraint as one of the hyperparameters, this is the percentage of the total constraint values, the sum of all constraint values for the items. So, for example, if there are 10 items with 10 constraint values each, which would add up to 100, and if I set the max constraint percentage to 0.5 or 50%, the max constraint will be 500. Of course, in that case, it wouldn't actually matter. Well, it would matter depending on the corresponding utility values, but anyway, you get the point. So the max constraint percentage will be used to set the max constraint hyperparameter by multiplying this value by the total sum of constraint values, generated constraint values. And so we start by importing stuff. This is all standard, or very normal and the same from before, and we import the functions. All of these are not new. Even this is not new. Compute average sum utility values. These are unnecessary. I was just testing something, and in this case, I'll be using favoring highs. Yeah, but I felt like importing all 10 procreate functions anyway, and I generate the items like this. no, this is the function. These are the new functions. First up is the generate items function, where it returns 10 items or 20 items, a given number of items, named item 1, item 2, item 3 to item n. And next up, just use that, use those items, or names of these items, and we can match that to the utility values generated by this function, which is this, generate util vals. We give it the number of items, and we specify what distribution we want to use. For instance, if it's normal, we will just sample it from a normal distribution. If it's log normal, we'll sample it from a log normal distribution. If it's uniform, from uniform. If it's exponential, we sample it from exponential. If it's Gauss, again, it's normal distribution, but I just put it there. Von Mies or von Mises, I don't know how you read that. We sample it from von Mises von Mises distribution. Pareto, Weibull, I don't know what that is. I'm ashamed to say, but I don't know all of these, or these three exactly. I don't know everything about these. And then if it's not stated, or else we just give it the normal distribution. Sample numbers from normal distribution. Yeah, and the same goes for the constraint values as well, except that the utility values, however, when the distribution is set to a normal distribution, for example, I just added 100 to the utility values, and also the same for the constraint values. These are all the same, just different function names. And the reason I added 100 is that when I use the selector function over here, I need the constraint values to be higher than 0, so that I need them to be higher than 0, because otherwise everything gets removed. Yeah, that's actually why. So I just added 100 just to where is it? What was I looking at? Yeah, I just added 100 just to make that happen. I don't think it will matter that much in terms of how the values are spread out. So, because everything will now be centered around 100. So, I tried setting the random seed, but I don't think it didn't work the way I intended, so I don't do that anymore. And I evolve for 10 items first. So I generate it like this. Items list 0, and then we have 10 items from item 1 to item 10. And we set the utility values like this by calling the function. And I just summed it up just for the fun of it. Also, the same goes for the constraint values. We call it like this, and then I summed it up. And then now that I have the total constraint, which is around 1000, and then I set the hyperparameters, and as I've said before, it is set at 0.5. Therefore, the max constraint is going to be 500.409 something, and number of items is still the number of items caps is number of items in small letters, which is 10 in this case, because I set it to 10. I know it's redundant, but yeah, I did that. And genome length, we've seen that. We've seen this. So generations, we do it for 500 generations, and the population size is 1000. And the rest is the same. We create the void genes, we create the genesis, we create the genesis 0, we create the genesis from genesis 0, and then we commence evolution. Yeah, great. Now, when we do this, again, Same procedure, result list head, result list tail, result list top 10%. And we store these values in these lists, and voila, after 20 seconds they're here. And the maximum ever was 503. And within the dictionary, after the final evolution, after the final generation of the final iteration, there were 965 entities. And this is kind of like a rough illustration of how these, how they were kind of distributed. I know I need to work on a better way of finding this, but this is happening mainly because the numbers are all in floats or decimals. I need a better way of doing this. This is crap. Yeah, I know. And if you look here, we go further, and then we see that the average peak is 503, and the average plateau is also 503. And these are the plots for the result list head, the top entities. As you see, it just goes straight up very soon, and then just stays there. Cool. And then this is the code for the result list top 10%, or the top 10% entities, the plots, and it climbs up, and then it stays there, and then the average peak and the average plateau are basically the same. The dip size and the dip percentage are just very close to 0. So no dip there. No dip whatsoever here at 10 items when normal distribution is used. We do it for 20 items again. Same procedure. So the max constraint is going to be 999 in this case, somehow. And when we do this, I am again. Did I forget to mention? Maybe I did, but I'll state again for the camera. The procreate function being used in this notebook and 3 others after this is favoring highs. So maybe I did mention it or not, but I'm mentioning it again. So I evolve with favoring highs. Took 35 seconds for 20 items. And here's the again distribution, but I don't like this picture. I need to work on a better way of showing that. And the average peak is 1009, and the average plateau is 1008. So not much difference there, obviously. And these are the plots for the heads, so basically just stay there. No oscillation whatsoever, it doesn't fall. And these are the plots for the top 10%. Average peak is again this, and the dip size is 0.5, 2, 3, 8, 1, 1 something, and the dip percentage is 0.05%. So basically no dip here until 20 items. We do the same for 30 items, and the hyperparameters being 1492, and where is it? And the maximum ever here was 1512. Again, distribution, I don't like it. The average peak was 1511, and average plateau was 1509. So okay. Also, almost no dip, as you can see in the heads and the top 10%. Almost no dip. And for 40 items, it's the same. Maximum ever was 2022, and the average plateau 2016, average peak is 2019. Almost no dip, again, for the heads, for the top 10%. And then I just jumped all the way to 100 items, which took 151 seconds on my laptop. That's not good. You see, this is nothing. I need a better way to illustrate this. I just didn't come around to doing it. So these are the results for the head. Same thing. And the dip size is only 24 as compared to 5,000 or 4,981. So the dip percentage is also very small, almost negligible. So and then I stopped here to think that is it that the normal distributions being used for the utility values and the constraint values are these distributions causing the no dip occurrence, no dip phenomena, or rather, let me just say, are dips caused by normal distributions that are not normal? Maybe. So I moved on to creating where is it? Oh God. Let me just load that up. Appears that I loaded the same notebook. So I thought, let's try another distribution, which is the log normal, and that's somehow, for some reason, very hard to say right now. Log normal, logarithmic normal. I need to speak to more people. Anyway, yeah, so I switched it. Guess what happened? Well, here, when I set the values, well, I didn't print it. Should have printed it. Anyway, when I set the values for 10 items, this is what happened. Again, that's very bad. When I set the values using log normal, the total utility value in this case, given the parameters for the log normal function, which were what? Where is it? There we go. Log normal. Mu is 3 and sigma is 1, as you can see here. So when I do that, the total constraint is 307, and the total utility is 310. Therefore, the max constraint is 153. And the difference between the values when I use normal and log normal is due to the 100 that I added to the normal distribution sampling. The 100 that I added when sampling from normal distribution. So anyway, max constraint is going to be 153.99 something. And when I do that, again, almost the same thing, just different, just sampling from, or rather, values sampled from a different distribution, that is log normal distribution. These are the plots for the heads, the top entities. These are the plots for the top 10%. Wow, almost the same. Weird. Let's look at 20 items. Heads, top 10%. Slightly more, but still the dip percentage indicates that it is also still, the dips are almost negligible, very small, below 2%. As I've probably said in previous videos, a dip percentage of 2 or around 2 or less is almost negligible. So yeah, it's arbitrary. I said that. Anyway, so let's look at 30 items. What is that? I don't know. But anyway, yeah, I need to work on that. These are the plots for the heads. So they're there. Maximum ever and average peak are these values. Where's maximum ever for 30 items? Is this 30 items? Yeah. Maximum ever is 971, and average peak is 959, and average plateau is 943. And when we look at the top entities, the plots for the top entities, the dip percentage is still 1.6. 40 items. Let's look at 40 items. These, again, heads, almost the same. Ignore the red line. The red line is at, set to y equals 1000 for some reason. I just wanted it there just to, see where 1000 is. And these are the plots for the top 10%. And the dip size is 19, and the dip percentage is 1.9. So again, negligible. Let's look at 100 items. Again, horrible plot. I'll work on it as I say that for the 1000th time. The plots for the heads, awesome or not awesome. They're just still there. And these are the plots for the top 10%. Again, 1.6%. Dip percentages equals 1.6. So almost no dip. So no dip. So why is this happening? Which is why I thought, let me try changing this value, max constraint percentage. So I just again, very arbitrarily, I'll need to do another grid search for this, but for now, for today, I just set it to 0.7, and I came back to using normal distributions again first, where I started. So for example, when I sample 10 items, 10 items, and the total constraint is again around 1000, so 0.7 gives us around 700. And when I run the code with this is what I get. Ignore the plot. These are the plots for the head. This will be these are the plots for the top 10%. So slightly more in terms of slightly higher dip percentage and dip size, but still we can say that the dips are kind of minuscule. So okay, let's move on to 20 items. This was for 10 items. This is for 20 items. Okay, this is the same for the heads, for the top entities. For the top 10%, yeah, these are the plots for the top 10%. Dip size is 28, average peak is 1329, average plateau is 1301. So dip size is 28.55, dip percentage is 2.14. So let's look at that. Let's look at 10 items again. 2.5% for 10 items, and 2.1% for 20 items. Maybe I'll still get almost the same results. But moving on to 30 items. Average peak was 1961, and average plateau is 1911. So previously it was the dip percentages were 2.5 and 2.1. almost negligible. And these are the plots for the heads, the top entities. These are the plots for the top 10%. And look, I'm starting to get dips. It is more visible right now. But however, it's still at 2.53%. So maybe not. I'm getting too, hopeful. Maybe I'm getting too optimistic, or not, depending on how I look at it. But if I want to know which distributions cause the dips, this is good, or this was good rather, or this is good. It depends on the time or the point in time that I'm trying to speak from. But anyway, timey-wimey, wibbly-wobbly. Again, dip percentage is at 2.53%, but I can still see it. But it could be because I have better picture, but I don't know. So 2.5%. Let's go to 40 items. The heads. See, now we are getting more oscillations in the heads, in the top entities. So this is a promising sign or not, but anyway, this is now certainly different. The plots for the top 10%, we do see dips, and now we are up to 2.92%. Cool. Now, let's look at 100 items. Horrible picture. These the heads, they oscillate a lot. Yup. But again, this could be because the pictures are somewhat getting more zoomed in, as I'm only adding 150 to the plots, and if the maximum ever is that big, that 150 is relatively small, and therefore we don't have a lot of space up at the top, which means that anything below the maximum ever will be magnified. So it will look as if there's more oscillations, but I don't know. Yeah. These are the plots for the top 10%, and voila. At 100 items, we do have a dip, 7.55%. So these are dips. So I moved on to using the other distribution, that is the log normal distribution, with a max constraint percentage of 0.7 or 70%. And for 10 items, heads, top 10%, the dip is at 2.41, so not that different. Before, with the normal distribution, it was 2.1 or 2.5 at this when given 10 items. With 20 items, heads almost the same. Now it's 3%. For the top 10% plots, we have a dip. We have dips, that are 3% in size, in change, at only 20 items. And then we look at 30 items. Definitely a lot more oscillation there, but again, it could be because of this. Anyway, and plots for top 10%. Now we have 5.3% in terms of change in size, change in values. Already at 30 items, it's at 5.3. So we can safely assume that there is a dip. But this one is quite interesting, this purple line. It actually never peaked at around the same time. It just peaked later. Interesting. Yep. Okay. At 40 items, so at 30 items it was 5.39. at 40 items, we go straight down to, well, hello heads, we go straight down to the top 10%, and now we have a dip percentage at the dip percentage at 7.85. And at 100 items, well, hello there. Look at that. Even for the heads, even for the top entities, we do see a dip. And for the top 10%, we have a dip percentage of 13.1. So it seems that distributions do kind of matter, and log normal distributions will make the dips even larger. However, the more important factor, the factor that plays a bigger role in whether or not a dip will ever occur or not, is the what I named here the max constraint percentage, as in what the max constraint or the constraint threshold and its relative size to the total sum of the constraints. So if the total, for example, if the total physical weight is at 1200 and the maximum constraint is set to 600, we might not get a dip. We might not get that big of a dip, or no dips at all. And however, if the max constraint percentage is set to 0.8, we will get bigger dips. But the strange thing here is that if the max constraint percentage is set to 1, there, I don't know, but I'm only thinking about this now. There won't be any dips, because you can just basically pack everything. You can just have everything, and the top entities will just be full of ones. So tomorrow, or when I work on this again, I'll need to do some kind of a grid search for 100 items, or maybe 40 items, or maybe 40 and 100 items, and see when dips actually start to appear and when they disappear. Whether starting from 0.01 or 0.1 to 0.2, 0.3, and then all the way to 1.0, figure out when they appear and when they disappear, or whether they disappear or they're not there first and then they appear and then they disappear. Yeah. So when dips happen or not. If the percentage is at 1.0, I don't think it will happen. It sounds obvious right now to me, but that might not be the case. I could be wrong. So that's about it. I have no idea how I'm going to name this video file, because I just somehow covered 4 notebooks. Yeah. Okay. So that's it. Thanks for watching. Goodbye. Peace.